Replication begins at the origin of replication, marked by a certain sequence. There, we will call that the origin of replication. An initiator protein will bind to here and begin the unwinding process. Helicase comes first, unwinding the double helix by breaking the hydrogen bonds that hold them together. The strand will experience some supercoiling, but that's relieved by the gyrase, which eases the tension in the strands. Single-stranded binding proteins, which I've labeled SSBP, maintain the DNA in each single strand by keeping them separated. RNA primase will put down the RNA primer so replication can fully begin. The primer is put down from 3' to 5', so I will label the ends like this. Notice the opposing ends because the DNA is anti-parallel. Replication happens from 5' to 3'. Replication will be continuous on the leading strand, the bottom one, and highlighted in blue, and discontinuous on the lagging strand, on the top and highlighted in green. I will start with the lagging strand because it's a bit more difficult. For the sake of not confusing myself or you with a cluttered drawing, I have omitted the gyrase and the single-stranded binding protein from the next drawing, but they are still there when this process happens in reality. DNA polymerase III attaches to the primer and adds nucleotides. Then phosphodiester bonds join these nucleotides together. Polymerase III travels all the way to the primer and stops. This stoppage creates a break, and the result of these breaks is called an Okazaki fragment, which is the region I have highlighted in pink. Polymerase I then comes and removes the primer and replaces it with DNA. To finish up, the ligase comes in and seals the strand by repairing nicks in the DNA. By comparison, the leading strand is quite simple. The replication is continuous all the way to the primer, and once the ligase seals off that strand, they break away.